In algebra, we sometimes use letters, which we call variables, to stand in for numbers. Remember, algebra is all about working with numbers. Logic is all about working with statements, and guess what? In logic, we use letters to stand in for statements. So we might have a compound statement like, James and Kate did their homework. And assuming that that means that James did his homework and Kate did her homework, and this is not an Alice and Bob had a baby situation, this is composed of two simple statements. We can represent each simple statement with a letter. So one simple statement is, James did his homework, and another is, Kate did her homework. We could represent the first one with the letter P, and the second one with the letter Q. This little loop on the bottom of the Q in my handwriting sometimes throws students off. This is a letter Q. I put a little loop on the bottom so that I can tell it's not a letter G. So if P represents James did his homework, and Q represents Kate did her homework, then the compound statement says, well, P and Q. And we'll get even a little bit more abstract than that in the next video. So often in various areas of mathematics, we have conventions for what kind of letters we like to use for our variables. In algebra, we like to use X, Y, Z, W, lowercase letters near the end of the alphabet. In logic, we like to use lowercase letters, depending on your textbook, but for this course, we'll like to use lowercase letters. From the middle to late part of the alphabet, the letters we like to use are like P, Q, R, S, T. If we need more than that, we might do L, M, N, O. We don't like to use O as a variable because it looks like a 0 and that's a mess. But P, Q, R, S, T will be our usual letters. And in fact, most of the time, P and Q, or on a really bad day, P, Q, and R will be enough for anything that we're working with in this class. We're using a lowercase letter from the late middle of the alphabet to stand in for a statement. In algebra, at some point, we say that our variables have a value. In logic, we say a statement has a truth value. We say that if the statement is true, it has a truth value of T, or true. If the statement is false, then it has a truth value of F, or false. Right, so true, it corresponds to what's actually happening in reality. False, it does not correspond to what's actually happening in reality. Now, in algebra, a variable can represent any number. And there are lots of numbers. So listing every possible value of a variable is not practical. In logic, there are only two possible values that a statement can have. It's either true or it's false. If it does something else, it's not a statement. Therefore, we can represent all possible truth values of our statements in a table, which we call a truth table. Now, what we're going to do with these truth tables is first we're going to create them, and then we're going to use them to do some sort of logic calculations. We'll see some examples of that a little bit later. But to begin with, we need to figure out how we start a truth table. Here's a truth table for one statement called P. So notice we have the name of the statement in the heading, and then in the column we have the truth values. And there are two possible truth values for a single statement P. What if we have two statements? Well, each statement has two possible truth values, but we end up having 4 rows in the truth table. These 4 rows represent the 4 possible combinations of truth values. So here we have P is true and Q is also true. P is true but Q is false. P is false but Q is true. P and Q are both false. And notice how we set this up. The Q column just repeats true, false, all the way down. The P column has 2 truths, so it has a true with each value of Q. And then it has 2 falses. It has a false with each value of Q. In general, so when we had one statement, there were 2 possibilities. With 2 statements, there are 4 possibilities. You might be wondering, okay, well, what if we had 3 statements? Well, if we wanted to put in another statement, the P column would repeat true, true, false, false. If we had more than 2 statements, we would keep repeating true, true, false, false down the P column. And in order to repeat that again, we would need another 4 rows. Every time we add another statement, we double the number of rows. So if we have n statements, there are 2 to the nth power possible combinations. There are 2 to the nth power possible truth values. And we will see some examples of truth tables with 3 statements later on in the course. We will see exactly 1 example of a truth table with 4 statements. You could, in principle, keep going up to any number of statements, but if you have more than 4 statements, you're going to want some techniques that don't require that you use truth tables.